Hello. In this video, we will talk about Bayes statistics and with a case study, which is estimating the bias in a coin. So first, we will review the Bayes rule, a Bayes formula. So Bayes statistics is the probability, which is a conditional probability. Conditional probability of C given R. So R, we call PR. This is called evidence. And probability PC if we have no information of any data of any R. So this is called the prior probability of C. Then this probability is a conditional of R given C. So the probability of R is the data, is the result given C. This C in the numerator is a particular value of C. And in denominator, the evidence, we can calculate it as a sigma summation of odd prior times odd likelihood. So this is also called the likelihood. So likelihood times prior summation of all the values of C, this is the evidence in the denominator. So the Bayes probability, or called posterior probability, is calculated as the particular value of the probability prior of C times the likelihood of this value C, given this value C, the results probability, then divided by the evidence. And next we take a look at the case flipping a coin. Actually, this case is very popular in the elementary statistics probability. So flipping a coin and get the result of a head or a tail, only two results. One is a head, one is tail. And we are interested in the probability of the parameter that will given the head theta. So this can be represented as the probability of gamma equals 1 given theta is theta. So what does this mean? So the left side is that because there is underlying constant probability of a theta will return the positive. Here positive is gamma equals 1, which is head. So the underlying the probability of giving a head, this value is theta, but the probability is how much is theta itself. So if we take, for example, theta is 0.5, so we can say given this 0.5 probability of giving a positive result, and we can get the head equals 1, probability is 0.5. So very simple, right? And we can also write the probability of giving a tail is 1 minus theta. So the probability of gamma equals 0 given theta is 1 minus theta. And we can also combine these two and written in one expression. So this is very often used in likelihood in statistics. And we can write probability of gamma given theta equals theta y power times 1 minus theta 1 minus gamma power. So what this means? So if gamma equals 1, so this part is 0. Is 1. So if gamma equals 1, which means we get a head, so the probability of head given theta is this term. Otherwise, if the gamma equals 0, so the first part is 1. So we can get the second one actually is this expression. So now for the case of using Bayes statistics for flipping a coin, so we have to define the prior first. So the prior is before we can get the updated credibility of the theta parameter. We have some assumption about this theta's probability. So for example, making the coin from factory, we have just a very normal, common understanding. So the factory will make this coin fair, right? So returning head and the returning tail will be very close to each other. So that means we have very high probability for returning the head is around 0.5, and a very lower probability of returning far above or below this 0.5 is very low. So which means if the total probability is 1 for categorical value of this theta, we have prior information that returning, for example, 0 is very, very low, and 0.2 higher than 0.1. Here is theta, right? So the probability of theta equals 0.2 is very low in the prior information. But probability of theta equals 0.5 is very high. Here can be 0.2, the probability, because the total of this categorical value for the probability will be 1. So for example, here 0.2, but for probability of theta equals 0.2 is 0.1. And is symmetrical, where 0.8's probability same as 0.2, and same as for the 0.4 and 0.6, they have the same probability. So this is the prior information. Then we will calculate the likelihood. So this is the likelihood function for multiple flipping. Because we have one likelihood for gamma, so here we write I for each result, because we can flip multiple times for the coin, and this likelihood function will be the multiplication or the products of each likelihood for each flip, right? Because they are independent. So independent, so that we can multiply together for the probability, then get the total, a whole likelihood function for multiple flipping. So the expression is just, we put this expression and with the product symbol. And because multiple head and multiple coin, multiple tail, we can sum together, then put on this power part. So in the end, actually is the theta, and with the power is how many heads times 1 minus theta, and times how many tails. You can see this is very similar as binomial distribution, right? Then, if we only get one flip, we will see how it is going with the posterior. So first, if we get only one flip and get the positive, or get the result is the head, so we can write, or just put in this likelihood. You will see different theta's various likelihoods, their value will be look like this. Why? Because if the theta returning head is 0.2, the probability of P of result head given theta, what's the value? Is theta itself, right? If we look back, this one, actually this is the likelihood for each head result, right? So the probability of head given theta is theta. So in the likelihood, if we get one trial and get the head, so this actually is the likelihood for each theta, right? So if the probability of given head is 1, so this likelihood will get is 1. If the probability of theta is 0.5 for returning a head, then we get the data 1, its likelihood is 0.5, is theta itself, right? So combining prior and likelihood. So we multiply together for each theta and divided by the evidence. Evidence is actually the summation of all products between prior and likelihood. So for each value, here the theta is 0.1, 0.2, 0.5, 0.9, and so on. So we just multiply all these theta and times the likelihood, right? And actually the likelihood is theta itself. So here is very interesting. So the theta times theta. So in this case, so we sum together and for the numerator, for each theta, we will get the result is also theta. So we will get each posterior for different theta value, right? So we will look at the posterior. This is the posterior. You can see the result will be little change compared with the prior, right? Because here we'll have higher likelihood. So because the old evidence will be the same, the denominator, but the numerator is different for each theta. For the large theta, for the small theta, they are different in likelihood times prior information. So we will get in the end the posterior is this map. And actually from the figure, prior, likelihood, and posterior, you can see the posterior is a compromise between the prior and likelihood. Compromise. So although we get, you can see, is a compromise. So not so excessive like this likelihood. Or this likelihood is just like a straight line. But combined with the prior information, the posterior is not like a likelihood one, but just is a between case between prior and likelihood, right? So this is a very simple case. Although simple, can show what the Bayesian statistic is. Then we will present more videos in the Bayesian statistics and for this playlist. And we have also websites for Python and R training, and there are lots of statistics examples if you are interested in.